Okay, so we're going to start off today talking about the electromagnetic spectrum. The electromagnetic spectrum is the spectrum of electromagnetic waves that we know to exist, okay? Now, there are definitely smaller waves of energy that are on this scale. If you think about de Broglie wave theorem and how matter and waves interact and complement each other. But the practical scale that we use for communication and in everyday life is right here, the electromagnetic scale. Now, I'm going to zoom down here and we'll take a look at it. First of all, the longest electromagnetic waves are radio waves. They can be up to miles long, all right? They go from miles long, radio waves go from being miles long, or 10 to the 4th meters, right? That's 10,000 meters long, to being this long, a meter long, all right? And then the shorter waves than that, see it says 10 to the 1st, 10 to the 0, that's a meter. So radio waves go from being miles long to about this long. Electromagnetic waves that are shorter than this are called microwaves. And microwaves go from being this long to 10 to the negative 3rd to being about a millimeter long, okay? Now microwaves are the electromagnetic waves that are in your microwave. That's why your microwave is called a microwave. Guess what else uses microwaves? Your cell phone. Good guess. Your cell phone. Your cell phone uses microwaves. So these are just descriptions of electromagnetic waves. And the only difference between the radio waves and the microwaves are their length. Okay? Microwaves, the smaller microwaves, are about the right wavelength to make a water molecule resonate. And that's how your microwave heats your food. It's really heating the water molecules in your food. All right? When you get shorter than microwaves, you're in the infrared waves. Infrared waves are just a little bit too long for you to see with your eyes. Cats can see a lot of them. Your cell phone can see them. Computer cameras can see infrared waves, but not your eyes, okay? And I'll prove that in just a little bit. Then we get to shorter than infrared waves. Then this little part right here of the electromagnetic spectrum, this tiny little space right here in the middle, these are the waves that you can see. You can actually see these with your eyes. You can't see radio waves or microwaves or infrared waves. They're too long for your eyes to register them. But right here in the middle, this is visible light. So we take this sliver of the middle between 10 to the negative 6 and 10 to the negative 7 meters. We take this and we spread it out down here. And we show you that visible light is Roy G. Biv, right? There's no indigo listed here. Red is the longest wavelength you can see. Violet is the shortest you can see. If you have a color that is violet and it gets to have a wavelength that is too short, or in other words, too purple, then you won't be able to see it. And that's called a UV, ultraviolet. Ultraviolet rays are damaging to your eyes because they can still get into your eye, but you don't notice them, okay? Ultraviolet rays have to be blocked by your sunglasses because sunglasses make your pupils open up more than they would be open, right? So they would be letting in more UV. So if you wear sunglasses, your sunglasses have to have UV protection, okay? Now, I'm going to give you this chart, everybody. This is part of your table, so I'm going to give this to you. Once you get waves that are shorter than UV, you have X-rays. X-rays we can use to see through your flesh and see your bones, right? And then shorter waves than X-rays, the shortest waves are called gamma rays. And notice that once you get below visible light, we call these rays. And when you have longer than visible light, we call those waves, okay? It's really just the same thing. So here's the deal. Students have asked me, Mr. Perkins, How fast does a radio wave go through space? Well, the answer is the speed of light. When we talk about the speed of light, or 3.0 times 10 to the 8th meters per second, or 186,000 miles per second, that's the speed of all these waves. Electromagnetic waves travel at the universal speed limit, which is the letter C, which is the speed of light. All right? So the longest waves are called radio waves. Shortest ones are called gamma rays. The one of these little bit right here in the middle is what you can see. All right? So that's the electromagnetic spectrum. Now let's talk about waves and what this must mean. So if I had a longer wave, we'll call this a radio wave. And over here, I'm going to draw a shorter wave. We'll call this, a microwave, or whatever. That actually is, there are microwaves that are literally this long. So we'll call this a radio wave, and we'll call this a microwave. All right? Now, if they're both traveling at the same velocity, all right, and that velocity would be the speed of light, right? So a better letter than V would be the letter C. The letter C is what stands for the speed of light, okay? That's not something you have to know for chemistry. I'm just trying to explain it to you right now. So they're both traveling at 3.0 times 10 to the 8th meters per second, right? Or the speed of light, which is called C. You know, E equals mc squared, right? You know Einstein's equation? This is the C. All right, if they're both traveling at the same velocity, right? And they have two different wavelengths, then they're also going to have two different what? Anybody know? All right, let's imagine that this is your eyeball. Okay? Look, there's your pupil. I'm going to give you some nice eyelashes. There you go. And here's your nose. And I don't know. You're happy that day? There. All right, now, I know that's terrible. I'm not an artist. But if you're looking at this radio wave, and it's traveling at the same speed, but it has a longer wavelength than this microwave, right? Move that bad boy. Then, let me make sure I'm still on my chart here. Then if you're there, what happens if you got your eyeball right here? What's the difference between these guys? These are twin brothers here, all right? All right? So we'll give these guys a direction. What's the difference? If they're both traveling at the same speed, but they have two different wavelengths, do you know what the one difference between these things is when it hits your eye? It's called the frequency. The frequency. The frequency is how often a wave hits your eyeball. Which one of these would have a higher frequency? That's right, the microwaves that have a higher frequency. This will be hitting your eyeball, da 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 da. This will be hitting your eyeball, da da. Does that make sense? Right? So longer waves have a lower frequency, right? They're all traveling at the same speed. Now, do you ever adjust the radio frequency in your car? Yes, it's called changing the radio station. Okay, you guys are so talkative. I need you, if you could hold it down and just like let me get some words out, I would really appreciate that. All the interruptions are just, it's driving me crazy. People at home, they're not talking. All right, so when you slightly adjust this wavelength, it's still traveling at the same speed, so it changes the frequency that hits your radio antenna. So 107.5 megahertz is a frequency. 97.3 megahertz is a frequency. Are you with me? So that is the electromagnetic spectrum. Okay? And we're going to need to understand that for the bigger part of our lesson. Okay? For the bigger part of our lesson. All right. And that's coming soon. All right. So we have got to talk about yesterday's lab, right? Yesterday's lab. If we look at yesterday's lab, I'm going to take you straight up to, in yesterday's assignment, here's a picture, right here. We burned some different elements. We put them up to a flame and got them really hot, and then they emitted different colors, right? Right? Okay. So then we found out that different atoms give off different colors of light. And why is that? Well, it has to do with what we call their alpha sequence or their electron configuration. Okay? And I'm skipping a lot of this stuff to get to this. An excited electron falling back towards the nucleus to its ground state will emit light. The different distances that this electron falls determines the wavelength and therefore the frequency of light. Longer distances will give you longer wavelengths of light. Shorter ones will give you shorter wavelengths, therefore changing the frequency. If you notice a drop from N4 to N2 here, shows you a greenish blue color. And we'll actually see how that works in just a second. Would you like to test the accuracy of this real quick? Watch, we can. N4 to N2, greenish blue. Do you agree that's falling like a greenish blue area here? Okay. So let's try it. On the back page of your chemistry reference tables, there's a chart. I'm going to have to shrink it up a little bit now because I got it too big. Have it too big. Now, this chart is Bohr's model of the hydrogen atom. This is the back page of your chemistry reference tables. And these circles are the different energy levels of an atom. And notice there's 6 circles. There really could be 7, but there's 6 circles here. So those are the top 6 periods of the periodic table. Does that make sense? Okay. In other words, if we're drawing a Bohr model, we draw more and more circles that add more and more dots, right? Now, electrons that have been excited and have been moved into higher orbitals than they normally would be, when they cool, they drop down to the nucleus as close as possible. That's called the Aufbau principle. When they drop certain distances through these different orbitals, they give off certain frequencies or colors of light. Let's find N4 to N2. See this N4? See we're in circle 4? And here it is. N4 to N2 gives us 486 nanometers. Let's go down here to the bottom, and you'll see that 4.86 will be just right here at 4.9. Do you agree with that? Look, that's greenish blue. Does that make sense? So, if we go back and look at this N4 to N2 drop, then this little GIF is correct. Does that make sense? All right. So, let's back this thing up. And have a quick review of yesterday's lesson. All right? And I'm going to make it pretty quick. Let's do a sodium atom, okay? Here's sodium. 2, 8, 1, okay? 2, 8, 1. 2, 8, 1. 1s2, 2s2, 2p6, 3s1, right? Wouldn't sodium be in 3s1 on the periodic table in that position, right? You remember that? Okay. So we've got sodium. Now, that atom, this Bohr model, and an Aufbau sequence ending in 3s1, okay? That's describing this sodium atom in its ground state. But we can excite it. We can give this atom more energy. We could put a flame under it and heat it up. Okay? Now, when this atom accepts energy in the form of heat, then these electrons have too much energy to stay this close to the nucleus, and they move further out. So, I'm going to change this model. So let's say we excited this hydrogen atom, okay? We added heat. Boom, heat. This thing absorbs heat. And now we get some crazy new, look, this is 2, 4, 4, 2, 4, 4, 2. What does that add up? 2, 4, 4, 2. That's 12. I got too many, don't I? How about this? 2, 4, 3, 2. So now this new, does that add up to 11? It does. So now let's say this sodium atom was in this ground state, which we can easily describe, and you've made multiple models of, right? Then we heat it up, and then these atoms move out, okay? And I'm just making these numbers up. These electrons, move out. And then now we take the flame away, and we let this thing cool off. Well, when it cools off, now it's going to go back to its ground state. So we're going to go back to a regular 1, 2, 3, 4, 5, 6, 7, 8. Now we're going back to sodium, okay? But notice this atom accepted energy in the form of heat, and it swelled up, right? And then now it's going to collapse back to its ground state when it cools off. How is it going to get rid of this heat energy? It doesn't give heat off when it collapses. What does it give off? Light. That's exactly right. So it absorbs energy as heat, and then it gives off photons of light. And those photons of light, if they had different wavelengths, would all be different colors. Does that make sense? And the colors that this atom gives off when it goes back to its ground state are very predictable because of where the electrons were and how far they fell. Does that make sense? Or through what energy levels they collapsed. So a sodium atom would do the exact same thing every time. So when we see this color pattern looking at a star, we know it has sodium in it, right? Now, the idea that these atoms drop back to their ground state and give off light, that is what the Aufbau principle is, and that's why we write Aufbau sequences to describe this. Are there Aufbau sequences for excited atoms? Absolutely. Do you do them in high school chemistry? Nope. You just need to know that an atom can get excited, and when it cools off, it drops back to its ground state, and it emits light. Does that make sense? All right. I'm going to stop at that.